Okay, yeah, so this is the problem that I encouraged you to have a go at the end of Friday's lesson, and those that weren't here, I'm sure you haven't had a chance to look at the video yet, but you'll see it at the end of that video. So if you grid out sec x minus tan x squared, you end up with three terms. Sorry, that's right, Ollie. You move my thing up right. Sec squared x we can integrate. It just becomes tan x, nice and easy. Tan squared x, well, we use the identity, which I've put on the board already, and that gives you sec squared x minus 1. So if I replace that with sec squared x minus 1, then altogether there I've got two lots of sec squared x minus 1. So that's good news. And this term, well, rings a bell. It's on the formula sheet. It's not straightforward though, is it? So we know that sec x tan x becomes sec x divided by 1, so just sec x. And that means that minus 2 sec x tan x becomes minus 2 sec x. So, here we go then. So that becomes 2 tan x, that becomes minus x, and that becomes minus sec x. And I forget, were there values to substitute in, or was it just an integration? I can't remember. It was one of the questions. We'll leave it there anyway, but that's that one. So integrating trig, we went through the basic reverse of the cycle. We looked at the formula sheet. We then looked at using the identities, and in particular using the identities for cos 2x to integrate sine squared and cos squared. And that was a crucial technique which is in the Friday lesson video, which I've sent out to those that weren't here. So I encourage you to look at that. We're moving on today. They're still integrating. I want this morning, to talk about some more integration, and this afternoon, because we're probably a little bit sick of integration, do a little bit of numerical methods stuff. I've been asking you to work through the numerical methods stuff on Uplearn. I certainly don't expect you to have done that, completed it by now, but I'm hoping you've done the stuff we're going to cover this afternoon, which is the iteration stuff, and in particular looking at the staircase and cobweb diagrams. So that's what we're going to do this afternoon. Today we're going to look at part 2 of how on earth do I integrate that. Okay, so if you remember, part 1 of how on earth do I integrate that sent us to page 6 and 7 on the formula book. And that's always where I would first go. If I got something, particularly something tricky, to integrate and I wasn't really sure, like, for example, sec x tan x. Always start with your formula sheet. But what about if the formula sheet isn't helpful? Well, okay, here's another potential for helping us integrate something we don't know. As is often the case, I'm going to ask you to differentiate 4 things for me. So I'm going to ask you to differentiate 4 things for me. So can I get you to differentiate those 4 things? Okay, so sine becomes cos, multiplied by what you get when you differentiate the brackets. ln becomes 1 over multiplied by what you get when you differentiate the brackets. This you multiply by the power, reduce reduce the power by 1 and multiply by what you get when you differentiate the brackets, 2x, so that actually becomes, 8x, 4 times 2x. And then power stays the same, multiplied by what you get when you differentiate the brackets. And of course you could write, the 2x afterwards, or that's fine. So we've already discussed how you can't integrate that because it doesn't become this because of the absence of the 2x. And you can't integrate that because it doesn't become this because of the absence of the 8x. And you can't integrate 1 over x squared plus 3. It doesn't become that because of the absence of the 2x. And you can't integrate that, just that, because of the absence of the 2x. You can do these things for ax plus b, ax plus b, ax plus b, ax plus b, but not if it's more complicated. However, what if you're asked to integrate something like this, or something like this, or something like this, or something like this? And so the how on earth do I integrate that part 2 step is realizing when you've got something which comes from differentiating something more complicated than ax plus b. So differentiating the sign of something more complicated than x plus b. Differentiating the ln of something more complicated than x plus b. Differentiating something in a bracket that's more complicated than x plus b, or differentiating e to a power of something more complicated than x plus b. And in those cases, you have to sort of reverse engineer it. And we're going to start by talking about the log ones, okay? Because what I've got here is something on the bottom, and on the top I've got what you get when you differentiate that something. So if I can sort of state that slightly more formally, what we've got there is the differential of something over something. And if that's something you're being asked to integrate, if you ask me to integrate that, then I know that's going to be my answer. So if you are asked to integrate a fraction where the thing on the top is the differential of the thing on the bottom, you know that must have come from a log. But what about if it looks a bit like that, but not exactly like that? So for example, I know if you ask me to integrate this, then that will be my answer. Those two examples there, they look a little bit like that, but they're not quite there. So just see if you can write down what those are going to be. Integrating this, I know is going to give me that, because I've just differentiated it, I've just gone the other way. So can you write down what you get when you integrate those two things which look a little bit like it? Okay, of course, when we're integrating, we still need the modulus sums. We still need the modulus sums. So that's the one we've already talked about. So this is just twice as much as that. So my answer is going to be simple as that. And this is half of that. So or ln of x squared plus 3, all divided by 2, whichever way you choose to write it. And so I think it's really good, and I've chosen this one to start with because this is the most common one. Really good to be able to spot when you're being asked to integrate something where the thing on the top looks a little bit like what you get when you differentiate the thing on the bottom. And when you see something like that, get into the habit of straight away thinking, right, is it a log? Is it a log? And the way I do it, I haven't got any clever way of doing this at all. I just say, okay, I think it's something to do with the log of 6x squared plus 3. So I'm going to differentiate that. I think this answer is going to be something to do with that. So I'm going to differentiate that to see what I get. So I get 1 over 6x squared plus 3 multiplied by what you get when you differentiate the brackets, which is 12x. So I know if you're going to ask me to integrate that, that's going to be my answer. I'm being asked to integrate that, which is 1/3 of that. So I spot that it's probably a log, so I differentiate the thing I differentiate what I think my answer is going to be. And once I've differentiated it, I can just tweak it a little bit. Okay? So I had to turn to another book to get a good set. So the top 6 here are examples of this type. But question 2 and 3 in this exercise are not examples of this. Sorry, yes, they are. Sorry, they're all examples of this type. I apologise. I'm just going to go and get the text. I've only got 3 textbooks from which this comes, so at least I can have a few copies out there. This comes out on the camera. I apologise. So yeah, so 1a, absolutely spot on. Comes out as just ln of x to the power 4 minus 1. 1b, spot on again. When you differentiate x squared minus x, you get 2x minus 1. Spot on. C, this is 15 times too small. If we differentiate the denominator, we get 15 x to the power 4. We've only got x to the power 4, so it's 1 over 15 times that, which you can write as that over 15. Absolutely fine. Except it's, as long as you make sure the whole thing, including the log, is divided by 15. I don't really like the way they work through this, but this is the answer. This is 3 times bigger than it should be, so the answer is 3 ln of all of that. And this is, if you multiply that out and differentiate it, you get 4x minus 1. So this is twice as big as it needs to be. So it's 2 times the log of that. And if you left that in its multiplied out form, that's absolutely brilliant. And then the last one, again, I don't do it the same as them. I just say it's minus 2/3. If you differentiate the thing in the brackets, you get 6x squared minus 9. They've got minus 4x squared minus 6, or plus 6. So you need to multiply by minus 2/3 to get there. So yeah, question 2. Even something as weird as this, and it's tempting to look at that and think that can't be a log, surely, but it is, because if I differentiate that, I get 1 over e to the x plus 6 multiplied by what you get when you differentiate e to the x by 6, which is e to the x. So that just is the ln of e to the x plus 6 plus c. I'll show the answers to the rest of 2 in just a minute. And 3a, again, tempting to look at that and think that can't be a log, but this looks a little bit like what you get when you differentiate that. So let's just try differentiating that. That's going to become 1 over 1 plus 2x. When you differentiate 1, it disappears. When you differentiate sine 2x, sine becomes cos 2x multiplied by 2. Bingo. So the answer to this is just ln of 1 plus sine 2x. So even weird and wacky things like that still come from a log. And rest of question 2, so in part B, you had, it was twice as big, so it was 2, no, sorry, it wasn't, it was exactly right. ln, I don't like the way they've set the working out, so that's that. In C, it was 3 times smaller, so it was a 1/3, and D, it was a half, so it was a half of that. And then 3B, it was minus a third. And if you got onto the last 2, well done, because they were, oh no, I only get B, that's fine. Okay. So this is a construct to look out for when integrating, and if you see something, even something that vaguely looks like what you get when you differentiate that, think logs. So what about the other things? Remember at the beginning we talked about 4 things that we can differentiate. So what about if we turn our attention to these ones here, okay? So here, when you differentiate a bracket, you end up with the bracket with a power that's 1 less, multiplied by what you get when you differentiate the bracket on its own. So that's not f dash of x, f of x, it's f dash of x, f of x to the n. I'm not going to write that formally because I think it looks a bit complicated. Let's look at some examples. If you flip over the page and look at the second batch of answers, second batch of questions, so that's exercise 8.5.2. Again, I look at that and I think, how on earth do I integrate that? Formula sheet hasn't helped me. It's not f dash of x over f of x, so it's not a log. But I can't help noticing that this 6x is not a million miles away from this differentiated, which would be 2x. It's a little bit fiddlier than the previous ones with logs, because what you've then got to think is, okay, what would that have been if it was something that I've just differentiated? If this was the answer to something that I've just differentiated, what would the bracket have been? And the thing to remember is it must have come from that. It must have come from that. To get this as an answer, we must have had a bracket with a power of 3, because in differentiating, we reduce the power by 1. So let's have a go at differentiating that. And I realise it's complicated. You know, you're integrating, you're differentiating, you're integrating, you're differentiating. I want to differentiate this, so that gives me 3 lots of the bracket to the power of 2, multiplied by what you get when you differentiate the bracket, which is just 2x. 3 lots of 2x, bingo. So that must mean that the answer to this is So these are a little bit harder to spot, I think, and they're a little bit more subtle, unless they're given to you all in a question where they're all, they're all the same. So have a go at that second block. So this is 852, the second half of the back of the sheet. Just be clear with D isn't a log because the 2x minus 1 is to the power of 3. So you've got to think of that as 2x bracket 2x minus 1 to the power of minus 3. Have a go. These are more complicated, but again, reverse engineer them. Reverse engineer them. Let's talk about B then. So when I differentiate x squared plus 7x to the power of 5, I multiply by the power, 5, reduce the power by 1, multiply by what I get when I differentiate the bracket, which is 2x plus 7. And I was about to multiply that out, but then I noticed that I'm being asked to integrate just that. That's 5 times too small, so the answer must be 1/5 of that. And if you don't believe me, then try and differentiate 1/5 of that. That 1/5 is a coefficient, so that's going to pass through unchanged. 5 times 5 is just 1. It does work. It does work. And for C, a similar approach. So the answer to C, you should end up with 1/16 of x squared, x to the power of 4 plus 4x squared to the power of 4. I'll just give you 2 more minutes and then we'll talk about the D, which is a fiddly one, and then I'll show you the answers to the rest. So with C, I differentiated that to the power of 4, which meant multiplying by the power, reducing the power by 1, multiplying by what you get when you differentiate the bracket, which when I sorted all that out, was 16 times bigger than this. So that means the answer to this must be 1/16 of that. And with D, the reason D isn't a log is because the denominator has a power. Okay, so the f dash of x, f of x thing only works when you haven't got a power on the bottom. So I've rewritten it in this form, and just like when I had this one, I tried differentiating that with the power 1 bigger. I've got to make the power 1 bigger here, which is fiddly, isn't it? 1 bigger than minus 3 is minus 2. So let's try differentiating this. Multiply by the power, reduce the power by 1, and multiply by what you get when you differentiate the bracket. Okay, I need minus 4x. I've actually got 2x, which is minus 1/2 times that. So that means my answer is minus 1/2 times that. Which of course you could write as minus 1 over 2 x minus 1 squared. Same thing. Same thing. I'll just show you the answers to the rest of that little exercise before looking at the third one. Sorry, I know we're moving at a fair old pace, as is often the case. Moving at a fair old pace, as is often the case. Right. So we've done, actually, we've done A, B, C, and D. So A was spot on, B was 1/5. I can't make that any bigger, so I'm sorry, that's probably not clear on the camera. C was 1/16. D we've just done, it was minus 1/2 times this to the power of minus 2. So if you got onto E, it was minus 2 times e to the 3x minus 5 to the power of 1. Oh, hang on.
There is a minus.
Yeah.
They've done that wrong, haven't they? Right, we're going to do that one in a minute, okay? So we'll come back and do that one on the board. Have they got this one right? Minus 1/6 cos 6 of x. Remember, to differentiate cos to the power of 6, cos x to the power of 6, you multiply by the power, reduce the power by 1, and multiply what you get when you differentiate the brackets. Right, let's go back and do e then. As
So G and H stuff.
sorry, yeah, hang on a minute. We're up here. So G, you had sec squared is what you get when you differentiate tan, so it was to do with tan 4x, and H. Oh, was H just spot on? Yes, yeah. Okay, so let's just double check E, because it looks like they've got E wrong. So E, I'm going to start by rewriting it as 6 e to the 3x times e to the 3x minus 5 power minus 2, which means that it's something to do with differentiating to the minus 1. So multiply by the power, reduce the power by 1, multiply by what you get when you differentiate the bracket, which is 3e to the 3x. So that gives you minus 3e to the 3x. So it's minus 2, lots of that. Yeah, that was just a... So it's minus 2 times that, which you could write as minus 2 over. So can we just look at 1 and 7 in the top block of questions on that side? So that's the 851. So we've looked at. Am I still recording? We've looked at two types from here. We've looked at the ones that become logs and the ones that become brackets. But we get a similar thing with trig. We get a similar thing with powers of e. Remember, when you differentiate a power of e, the power doesn't change, but you still multiply by what you get when you differentiate the power. And here, when you differentiate trig, you've got to go around your circle, but you still multiply by what you get when you differentiate the bracket. So, question 1. You've just got to be willing to say, oh, do you know what? What would I get if I differentiated e to the x squared? What would I get if I differentiated e to the x squared? And we know that the power stays the same, but we multiply by what we get when you differentiate the power. Bingo. Bingo. So the answer to that one is just e to the x squared plus c. And with number 7, just got to say, oh, do you know what? What would I get if I differentiate cos of x to the power of 4? Sorry, it's not cos x to the power of 4, is it? I've got to think that may well have been something to do with sine x to the power of 4. So what I'm thinking is, because when you differentiate sine it becomes cos, what would I get if I differentiate that? Okay, well, sine becomes cos, multiplied by what you get when you differentiate the brackets. It's not bad, is it? It's not far off. This is 4 times smaller than that, so the answer must be a quarter of that. See if you can have a go at the rest of that exercise. And what I'm going to do is attach this, put this sheet on class charts with the answers to this third exercise, in the hope that, we've only got 5 minutes left. So, in the hope that you'll have a go at some of those independently. Those are probably the trickiest of the lot. They're harder to spot. But I'm going to do that right away so I don't forget.